Module 1. Why DNP3 exists. The utility communication problem. 1.1. The modern utility data challenge. Evolution of utility operations into data-centric systems. Electric utilities historically deployed communication systems primarily for real-time control and monitoring. Early supervisory control and data acquisition, SCADA systems, were designed to answer narrow operational questions: breaker open-close status, basic analog measurements, and alarm signaling. Over time, this scope expanded dramatically. Modern utilities now operate highly distributed, data-intensive infrastructures that include transmission SCADA systems, distribution automation DA networks, substation automation systems, SAS, intelligent electronic devices, IEDs, remote terminal units, RTUs, data concentrators and submasters, enterprise analytics, planning, and asset management platforms. These systems are no longer isolated operational tools. They function as strategic data sources feeding reliability analysis, predictive maintenance, regulatory reporting, outage management, market operations, and long-term grid planning. Explosion of device diversity. Utilities are integrating data from devices that differ across multiple dimensions: vendor origin, hardware capability, communication media, serial, radio, fiber, cellular, IP, processing power and memory constraints, data semantics, and update rates. Each new generation of devices introduces additional data points, status flags, analog measurements, counters, event logs, timestamps, and waveform records. This heterogeneity creates a scaling problem when communication methods are not standardized. SCADA, DA, and SAS as data assets. In contemporary utility environments, SCADA systems act as central data aggregators rather than simple control consoles. Distribution automation relies on near real-time event reporting to isolate faults and restore service. Substation automation systems generate high-resolution operational data from protection relays and monitoring IEDs. The value of these systems is increasingly derived from data accessibility, integrity, and interoperability, not merely command execution. Limitations of proprietary and legacy protocols. Prior to standardization efforts, utilities relied heavily on vendor-specific proprietary protocols, custom or undocumented message formats, point-to-point integrations tightly coupled to specific hardware. These approaches introduced several systemic problems: integration bottlenecks when devices from different vendors needed to coexist, high engineering and maintenance costs for protocol translation, vendor lock-in that restricted future expansion or replacement, inconsistent data representations across systems, limited scalability across wide-area communication networks. As utilities expanded geographically and technologically, these limitations became untenable. Requirement for open, interoperable communication. The modern utility communication problem crystallized into a clear technical requirement set: non-proprietary protocol specifications, multi-vendor interoperability, deterministic and reliable communication over imperfect media, efficient handling of low bandwidth and high latency links, native support for both polling and event-driven data exchange, clear data typing and standardized object definitions. This requirement space directly motivated the development of a protocol purpose-built for utility operations. TAC 1.2, Emergence of DNP3, Origin and Initial Development. Distributed Network Protocol version 3, DNP3, was developed in the early 1990s by GE Harris Energy Control Systems, originally operating as Westronic Inc. The protocol was engineered specifically to address the communication challenges observed in electric utility SCADA and automation systems. Unlike general-purpose networking protocols, DNP3 was architected with utility field conditions in mind, including unreliable communication links, low data rates, and geographically dispersed assets. Transition to open governance. In 1993, ownership and stewardship of the DNP3 specification transitioned from its original developer to the DNP user group. This transition was critical to the protocol's long-term adoption. The DNP user group assumed responsibility for maintaining and evolving the protocol specification, publishing technical bulletins and recommended practices, ensuring backward compatibility across revisions, balancing utility user requirements with vendor implementation realities. This governance model ensured that DNP3 remained open, vendor-neutral, and utility-driven. Design philosophy. Aligned with utility operations, DNP3 was explicitly designed for master outstation communication models, wide area utility networks, deterministic control and data acquisition, efficient transmission of small structured data objects. Key design assumptions included communication channels may be noisy or intermittent. Devices may have limited processing and memory resources. Data changes are often sparse relative to polling frequency. Time-stamped events are critical for post-event analysis. These assumptions fundamentally shaped DNP3's layered architecture, object model, and event-driven mechanisms. Relationship to international standards. DNP3 drew foundational concepts from early work by IEC Technical Committee 57, particularly the IEC 60875 series. Both protocols were later incorporated under IEEE 1379, reinforcing DNP3's standing as a recognized utility communication standard. While regional adoption patterns differed, DNP3 achieved particularly strong penetration in North America and other regions with similar utility architectures. Widespread industry adoption. By the late 1990s and early 2000s, DNP3 had been implemented in thousands of substations, been embedded in RTUs, IEDs, relays, meters, and concentrators, achieved broad vendor support across the utility ecosystem, become the de facto standard for SCADA and automation communication in many utilities. Its success was driven not by theoretical completeness, but by practical fitness for real-world utility networks. Position in the utility communication landscape. DNP3 emerged as a protocol that addressed immediate operational needs while remaining extensible for future requirements. Its emphasis on interoperability, reliability, and data efficiency positioned it as a foundational technology for utility automation systems transitioning into data-centric infrastructures.